Thank you. And actually, the 60-based counting reminds me of T.D. Lee's 60th birthday celebration, which was just as I was arriving as a young postdoc at Columbia. And I remember one phrase that he said, which is that happiness is when old friends come from far away. And I think we're not quite at 60 yet, but it's probably appropriate for this gathering as well. So I'd like to start by thanking the Mani Al-Baumic Institute for hosting what, at least for me, has been a very entertaining and enjoyable conference thus far. And also thank the organizers, Jungbo and Zvi, for the opportunity to speak here. So we all know that the universe had a very violent origin. And it remains a very violent place today. Now, everyone, I believe, likes black holes, but we also have to admit that a lot of that violence is associated with black holes. So if you imagine, for example, taking a small black hole, maybe 3 solar mass, black hole eating the Earth, so it's about the size of Paris, about 9 kilometers, the Schwarzschild radius. And this is probably one of these imaginary experiments that should stay a Gedanken experiment. You shouldn't actually try to do this, even if you could. Anyway, there are calculators online which will tell you roughly how much energy would be released, and it's of order a few times 10 to the 40th joules. And just for standard of comparison, over the lifetime, the sun will emit about a few hundred times more than that. Now, if we go up in scales, then a supernova will release about 100 times more, and most of that is in neutrinos, but still the peak visible luminosity is comparable to that of a galaxy, which is how we can see supernova, isolated supernova in distant galaxies. And then going up to the local supercluster, it's again an increase of a little under 6 orders of magnitude, but we have to go many orders of magnitude higher to get to the peak luminosity of a 30 solar mass black hole merger, which is kind of the size of the first one that was seen by LIGO back in 2015. And all of that emission was invisible until recently because it's all in the form of gravitational radiation. And we have the collaboration, LVK collaboration, which has collected over 90 events since their first announced event just under 8 years ago. They're currently in their 4th run, and they will probably be running until the end of the decade. Most of what they've seen are binary black hole mergers with a handful of neutron star or mixed mergers. And that's nicely shown in this kind of bat-shaped diagram. All these blue circles are black hole mergers, and then there's a handful of neutron star or neutron star black hole mergers down at the bottom. This is, again, taken from the LVK collaboration. So as most of you have probably seen before, these are interferometers. Each of them has 2 arms. The big one is LIGO, which has 2 sites in Louisiana and in Washington. Virgo is outside Pisa, and most recently, Kagra, which is underground in Japan, has joined, although I think they're really still in the commissioning phase, so it may be till the next observing run before they really contribute significantly to the observations. Maybe there'll be an Indian one that joins within the next few years, but otherwise there'll be newer detectors in the next decade, which I'll come back to mention at the very end. So from a science point of view, then, of course, they would like to determine the presence and the distribution of heavy compact objects, and they've already found this completely unexpected class of black holes, tens of solar masses, and in fact, indeed, even binaries of these black holes. No one really was expecting that ahead of time. And so with increased sensitivity, increased data collection, there's always chances for more surprises. For neutron stars, which was kind of the classic goal, that's what they expected to see, then we'd like to determine the equation of state, which is a long-standing puzzle in nuclear physics, and also has implications for the very Earth on which we're standing, because the transferic element production, some of which may have ended up in the Earth, is determined by that. One can also expect to do strong field tests of Einstein's gravity, and maybe more speculatively, to have some insight into quantum gravity in the next decade. So what does a theorist do in this domain? Well, the first thing that we have to understand is that we're doing interferometry. They're measuring essentially strains, displacements that are way smaller than the size of the proton. But even then, you're starting with raw signals that look like this, and then they do a huge amount of filtering, and then you get something that looks like this. And if you'll notice the scale here, it's 3 orders of magnitude of filtering, but then the signal that you're actually interested in looking at is something like this. So you can't just look for the signal. You have to have some idea of what it is you're looking for. You have to look at internal correlations of the signal. And that's done using templates. Templates, in this case, for binary inspirals and mergers. And ultimately, once you've found an event, you also need these templates in order to measure the parameters, the masses, the spins of the mergers. And in fact, the precision templates that you want for future physics is really to do precision measurements. That's in some sense where the bulk of the theoretical interest is. So what's the basic setup here? I mean, there are other classes of objects that they can look for. Things like, for example, mountains on neutron stars, which a mountain on a neutron star is something that's about 1 millimeter high on a 10-kilometer radius object, but I'm not going to refer to that. So we have 2 slowly inspiraling compact objects, for example, black holes. And in the inspiral phase, it's weak field perturbation theory, so we can use perturbation theory there. The actual merger is now strong fields, and the only technique we really have today is numerical relativity, which is computationally very expensive. So you can use it as an occasional reference, but you really want to have other techniques. And finally, let's say you have 2 black holes that merge into one black hole, the resulting object will ring and emit a further train of gravitational waves. And that's something that you can do in perturbation theory about using the normal modes about a black hole. It's a complicated but different subject. And this has been a long-standing subject for general relativists over many decades, and at least the formalism that people in the amplitudes community are probably most familiar with is something called the effective one-body formalism, which is originally due to Alessandro Bonanno and Thibaut Damour. And then, of course, there are contributions from numerical relativity, but again, that's fairly computationally expensive, so you can't just run lots and lots of templates numerically. So about 20 years ago, in pioneering work of Walter Goldberger and Ira Rothstein, they observed that you could use ideas from effective field theory, taking advantage of scale separations, to do these computations more effectively and more easily. So at this point, though, you're probably wondering, what's going on here? I mean, this is all very entertaining. At least I hope that some of you think it's all very entertaining. But we seem to be heading towards a talk on general relativity. And so, of course, the obvious question is what is this doing in a conference that is celebrating 50 years of QCD? Did I walk out of the elevators and take a wrong turn? So, no, I didn't. But in order to understand that, we should go back and look at somewhat more recent history than the focus of the early years of QCD. So we've heard a lot already about the early successes of QCD and then the following years of calculations of basic processes and corrections. And somewhat later, people started to look at multi-jet production, and in particular, starting to look at 2 to 4 processes. So, for example, 2 gluons coming in and 4 gluons coming out, which would give you the leading order picture of 4-jet production. And it wasn't obvious at the time, or at least, well, we would have to ask personal reminiscences of people who were there whether they expected something to come out or not. But the thing that came out was incredible and unexpected simplicity. So part of that simplicity came from looking at helicity amplitudes, which is, again, something that has its roots with Bjorkane in the 1960s. And there were many ways of implementing them, but I think the one that is so-called the Chinese magic of Shu, Zhang, and Chang is the one that really endures. And that's also kind of an interesting historical footnote, maybe, that this was really just a few years after the terrible intellectual and personal destruction of the Cultural Revolution, and there were already some frontier flowers of science that were emerging in China. Anyway, there's the celebrated Park-Taylor amplitude. I assume that most people in the audience know what these angle brackets mean. They're spinor products. If you don't, you can just think of them as square roots of Lorentz invariants. So this was an amplitude where you could essentially write down the answer for an infinite number of Feynman diagrams on a single line. And that's certainly about as simple as you could possibly have hoped for. Now, it's also true, one has to note parenthetically, that Park and Taylor did not actually write down the Park and Taylor amplitude as we know it today. It's written down by Mangano and Shu along with Park. But this is the form in which we know it today. And that amplitude planted a seed. So it's something very simple, and if we follow a saying, which at least I've heard attributed to Feynman, that simple results should have a simple derivation, then it was the signal that there should be more things to look for, and we were really at the start of a new era of computing QCD amplitudes. Now, in spite of the fact that there was a lot of very important early work on QCD at Harvard, by the time I got there, no one was doing perturbative QCD. In fact, my only exposure to it was in a special topics course from John Preskill. He was a wonderful lecturer, by the way. And it's the working on perturbative QCD afterwards, and certainly trying to do it by applying perturbative string theory, is something that my thesis advisor has never forgiven me for. But I pursued that path anyway. So it was left to Parameshwar Nair, who was then a fresh assistant professor at Columbia, to get me started on this path. And beyond that, he, and among his many other original contributions, he was also the person who understood how to phrase the Park-Taylor amplitudes as correlators of complex projective space. And that, in turn, was the underpinnings of Witten's twistor string theory, which played an important role in the early 2000s in expanding the community of people working on the subject. Anyway, I mean, tree-level amplitudes was very nice, but ultimately we wanted to calculate loop corrections. And after a number of other things, then this is Tzvi and Lance and Dave Dunbar and I came up and were able to formulate the unitarity method for doing one-loop calculations. And that, in a sense, was the birth of scattering amplitudes as a subfield. And so one of the key themes then, and has remained a key theme going forward, was to focus as much as possible on physical on-shell quantities and even in intermediate steps. And after a few years, we went from unitarity, which is pretty much what you think of it as. You can think of it as applying traditional dispersion relations, going on to generalized unitarity, where you cut any propagator and then match the analytic structure in order to extract gauge invariant coefficients of basis integrals. This is something which Babis already talked about at greater length in the morning. Now, it took a while before the community realized that there was actually something interesting and useful here, so we had to traverse a bit of a desert, and it was very important as young people without permanent jobs, except for Lance, that we needed a protector. And in addition to his intellectual leadership in perturbative QCD and later in quark-gluon plasma, we were very fortunate to have Al Mueller playing that role. And I'm sure you've seen his name already cited in many citations in earlier talks in this conference. It was also important to have enthusiastic senior colleagues who were actually working on calculations and both competing with us and encouraging us, and it's a great pleasure that I see Zoltan, who was an important person in that respect, sitting in the audience. I should mention that George Sturman was also very enthusiastic and encouraging, although he wasn't actually working directly, either competing or kind of paralleling us. Anyway, initially it was too hard to do full QCD, so we went into the theorist's laboratory, which is the n=4 supersymmetric theory. And again, that's something which there's been a complete reversal of the way, at least we think about it, that instead of being a theory that was vastly more complicated, it's actually a theory which is much simpler because it has higher symmetry, and that higher symmetry is reflected in the simplicity of its scattering amplitudes. And it's been a great laboratory and development environment ever since. So we applied the original unitarity method, basically summing over all the possible cuts, and for the same helicity configuration that goes into the Park-Taylor amplitude, and thanks to the knowledge of the all multiplicity Park-Taylor amplitude and its simplicity, we were able to do the sums, and again, compute this object at all multiplicity, and you get an amazingly simple result. There's a prefactor which is the same as the tree amplitude, and it's multiplied by a very simple weighted sum of two-mass box integrals. And these actually happen to be the simplest box integrals to calculate. Now, today, this calculation has become even simpler. It's really a student exercise. And it's not because the students are better, although with some humility, I should say that certainly today's students know more than I did at at this stage of their career, it's because the technology has gotten better. And going from the original unitarity method to generalized unitarity, in this particular example, it would mean matching the cuts, or in fact, just doing a quadruple cut. So these correspond to complex residues of the original integral or the original amplitude off in the complex, out in complex C4. And then the residues are just products of tree amplitudes, again with complex momenta playing a very important role. And that product simply reconstructs the Park-Taylor amplitude. So after a number of years of hard work, then eventually we're able to produce, and other people joining in the adventure, able to produce new results, and also showing that instead of taking a decade to add a leg, it would be a matter of a year, or in fact with automation, basically just dependent on your computing resources. And this is a summary taken from a talk by Gavin Salam in 2012. And of course, we've already heard that both from Thomas and from Babis, that some of these ideas at higher multiplicity at 2 loops are continuing to play a role. And there's other ideas in terms of understanding how to deal with the integrals that have maybe taken center stage for the 2-to-2 processes. So one of the things that I think is interesting is that you can look at the scattering amplitudes program in a sense as taking Landau seriously. And this is a quote which Bob Jaffe showed in his talk, which I actually had not seen before, but it's really a great quote. And indeed, we take the scattering amplitudes to be the fundamental quantities, the only fundamental quantities, and they are determined by unitarity and locality. Now, unlike Landau, where we go 180 degrees from him, these ideas are adopted not as a rejection of quantum field theory, but as a distillation of their essence. And so it's interesting how some aspects of these ideas in a period where people were trying to throw field theory away actually have survived. And there is by now an annual conference with over 200 attendees and a lot of enthusiastic younger people working in it, and very exciting developments all the time of new tools to go into new calculations, to then be recycled into new understanding of structures. So there's, of course, standard recursions for the trees and integration by parts, which again Babis talked about, and differential equations, which play an important role and are in some sense the key difficult part in pushing at the moment to higher loops. There's really interesting new ideas on finite use of finite fields and rational reconstructions, so reconstructing analytic expressions from numerics, and a growing understanding of all sorts of structures that are underlying amplitudes. And some of these have an echo in other applications. So to come back to gravitational waves, again, the traditional approach would have been to solve general relativity perturbatively, maybe to use effective field theory to organize that calculation in a better way. But one can think also about using scattering amplitudes. And some of the early motivation for that came, in fact, from one of the key figures in general relativity, that Thibaut Damour himself suggested that the amplitudes people use their novel techniques to compute the 2-loop scattering amplitude and thereby deduce a certain contribution. there's a certain impedance mismatch in the language where you see this very strange post-Minkowskian phrase. You should just understand that as the third order in perturbation theory. There's nothing more deeper than that. Now, this isn't an obvious thing to be thinking because scattering, we're ultimately interested in a bound state classical problem. Scattering amplitudes are unbound and deep in the quantum regime. So how can they help? Well, first of all, there's the philosophy of the scattering amplitudes program that we're really focused on gauge invariant, kind of infrared safe quantities. There's the powerful toolkit that has been developed for both for doing the amplitudes and doing the integrals. And but that's a little bit thin as motivation for kind of working very hard and trying to cross a field with the danger of Swiss cows perhaps butting you in the back. Although generally my experiences in Switzerland has been that the cows are pretty docile, but still the key thing that is really crucial, and it was I think the motivation for many people, was something known as the double copy, and that's qualitatively the idea that amplitudes in gravity are in a certain sense the same as amplitudes in Yang-Mills squared. And that's not at all obvious if you look at the Lagrangian or if you look at the Feynman vertices. You can go pull out the vertices for gravity from a mid-60s paper of DeWitt, and the three-point vertex, even in this very compact form, looks a lot more complicated than the Yang-Mills, and certainly that's true of the four-point vertex, and there's an infinite series of further vertices to look at. In fact, it's even more complicated than it looks because each of these p symbols is actually a sum over permutation. So if you were actually to write out all the terms, it would really be an unholy mess. So if you go on shell and you use complex momenta and spinor products, then the three-point amplitude in Yang-Mills is this very compact object. And the same is true in gravity. And in fact, the gravity three-point amplitude, I've of course stripped the couplings here, is literally the square of the Yang-Mills coupling. So here it's not just figuratively, it's literally. And the double copy is the field theory equivalent of the Kawai, Llewellyn, and Tai expression, where you can write closed string amplitudes in terms of open string ones. And again, it's one of these accidents of intellectual and scientific history that the string ideas, which are actually much more complicated, are the ones that came first. So we know how to generalize this to higher multiplicity at tree level. In fact, it's even proven. And via generalized unitarity, the same technology can help us compute loops more easily. So the in-spiral people usually think about computing in the so-called post-Newtonian approximation, so where you're doing also an expansion in velocity, because until the last few orbits, the velocities are actually not that high. But of course, with amplitudes, we're going to be doing fully relativistic calculations, or at least that's what we'll admit in public. By now, this is already 2022, the state of the art for the perturbative calculations are in the red box. The intersection of that with the dark green is what is known in a sense through the post-Newtonian, and the light shaded part is what you'd like to know for future precision perhaps for '05 and certainly for future generations of gravitational observatories. And these last two lines here, the G cubed and the G fourth line, that's stuff which, in a sense, was certainly beyond what the GR people could do 5 or 6 years ago, and that's really contributions from the amplitudes community. Now, this suggestion led to a huge flurry of activity. Again, at least for me, starting at a completely unrelated program at the Kavli Institute in 2018. Most of this I won't have time to talk about, but there's a huge variety and richness of ways people are thinking about this. So in the weak field regime, there are 3 distinct scales that one can think about. There's the size of the black holes of the compact objects themselves. There's the separation of them, which is going to be much larger than their radii. And then there's going to be the wavelength of the emitted radiation, which is going to be larger again. And one can use that to write down an effective field theory. And in this context, as I mentioned earlier, it originated with Walter Goldberger and Ira Rothstein. But of course, there's always an enormous intellectual debt to Steven Weinberg, and I suppose I should also say to Ken Wilson standing behind that. So the setup is that we're at least directly not able to do the bound state problem yet. So we're going to look at the unbound, the scattering problem, and we're going to scatter 2 things. And it turns out that, at least for non-spinning black holes, you can model them at up to a fairly high order just as point particles. So we're going to scatter 2 point particles. And the direct approach is to interface with what people do in GR, which is to compute corrections to the Hamiltonian, or actually more properly, corrections to the potential. And so they knew 2 orders, and we'd like to add more orders. And then once you fix the potential via scattering calculations, you can turn around and apply it to bound state calculations using that Hamiltonian. In the context of conservative quantities, so 2 to 2 quantities, then it's also understood how to do that by analytic continuation in the angular momentum, or if you like, in the eccentricity. And it's one of the open subjects is how to do that for directly for processes that also include radiation. So the basic approach is to compute the scattering amplitudes in an effective theory that's built out of the potential, and then you match coefficients to the classical scattering amplitude in the full theory. That classical scattering amplitude you get by computing the quantum scattering amplitude and taking the classical limit, and that was a program that was outlined by Michael Salon, who's actually here at UCLA, and 2 of his then more senior collaborators. So the infrared singularities, which of course are always present in scattering amplitudes, cancel in this matching. The effective theory calculation is itself pretty simple. The hard work is actually in doing the gravitational amplitude calculation. And we had the very dramatic and result in 2019 from Mao Tsung, who's today in Edinburgh, and again, Mikhail Chao Shen, who's on his way back to Taiwan, and their more senior colleagues, one of whom is sitting in the audience, but probably won't be upset that I'm emphasizing the younger people. And then they were able to follow that up This is a 2-loop calculation with a 3-loop calculation for the order g to the 4th contributions. And again, in these calculations, both the double copy and generalized unitarity play a key role. So the same ideas out of the early days of scattering amplitudes have remained important tools going forwards, and they're actually working on the next order, but if you want to know when they'll finish, you know who to ask. So this is something that, because you're linking with the formalisms that are used by the GR people, you can actually make direct contact. And so in neutron star mergers, you'd actually have many, many orbits, but in many black hole cases, you don't actually have that many orbits. So all of these corrections are actually important. And in this business, in some sense, the gold standard, the truth, what you're comparing to is not so much observation or data, because there's a lot of unknown parameters. What you compare with is results of numerical relativity, which is here listed as NR. And you can see that as you add more and more perturbative contributions, then you get closer and closer, so you're matching up to really almost the last orbit and a half. There's a certain amount of alchemy that goes into what's known as the effective one-body approach, where you have some parameters and you match them to NR, and so you're effectively doing some sorts of resummations. But and that's how that actually gets closer to the NR result than just the pure perturbative ones. But nonetheless, these higher order perturbative contributions with certain resummations that are part of the EOB framework really let you get very, very close to the numerical relativity results, even as you're getting very close in. And this is actually a paper from Damour and Retegno from late last year. Again, these points here are from numerical relativity. And for PM here, again, just read orders in perturbation theory. The x-axis is actually angular momentum, but you can think of it as getting closer in as you're moving to the left here. So that's one out of one of the major approaches, and I wanted to spend really just a couple of minutes. I guess I have what, about 5 minutes? Okay. Talking about a less direct approach, but one where you ultimately have an approach that should be able to compute the quantities of interest directly rather than by matching to a GR Hamiltonian. So the idea here is that you want to pick observables in the quantum theory that are also relevant classically. You re-express them in terms of scattering amplitudes, and then you take their classical limit. So you restore h bar, you rescale the couplings properly, and kind of the other critical step in terms of organizing the integrals is to replace the photons and the graviton momenta with wave numbers, and that allows you to do the h-bar counting properly. So we're not interested in plane wave states the way that, we are in ordinary, let's say, collider physics, so we have to build wave packets. And then if we want to evaluate, for example, the final momentum of one of the particles, we're scattering two massive particles, then we simply evaluate the momentum operator in the out state. And one of the key points here is that we think of the S matrix as being an evolution operator from the far past to the far future. So we can then write everything. We can write our expectation value of the momentum in terms of the in state where we control the wave packets which are shaping the particle. And if we then look, let's say, at the impulse, that is the difference between the final momentum and the initial momentum, and we rearrange it a little bit using unitarity, then we get an all orders formula which has one term which is linear in the T matrix and one term which is quadratic. This term, in a sense, is the virtual contribution, and these terms are the cut contributions. So the impulse is, at least classically, is in a certain sense a global observable, but we can also look at local observables, and that's ultimately the kind of thing that we're interested in doing. We have some scattering, and we idealize it by imagining there's some interactions in there, and then afterwards the radiation will propagate out to a detector. I mean, if it were electromagnetic radiation, we could use the Mark I eyeball, but clearly for gravitational radiation, we need something a little bit more sophisticated. And the waveform is the leading part of the large distance behavior. Anything that's 1 over x squared or higher is just not going to be visible. So again, we can, for example, measure the Riemann tensor or some spinorial analog of it. In the out state, we rewrite that in terms of using the S matrix, and then we can rearrange things to write it again in terms of a term which is linear in the transition matrix, or a term which is quadratic, again, virtual and cut contributions. And these are all orders formula. You can now start to expand them perturbatively. At the lowest order, in fact, only the first term contribute. It's something that's linear in an amplitude, so there's the amplitude with its delta function sitting there. And the key point here, without going into all the details, is that the waveform is essentially a 5-point amplitude. So what we're trying to compute here, at least in the scattering regime, is a 5-point amplitude. And so as we're not that far from Hollywood, then it seemed appropriate to end the talk with a short clip, not necessarily up to Hollywood special effects standards, but I hope you'll find it entertaining. And this is one that I have gotten courtesy of Radu Roiban. And so this is showing the metric from the leading order waveform as it goes by. At leading order, this is in fact a calculation that dates back to the 1970s, but the next to leading order ones, which are currently people have worked out, those are completely new results. And with that, let me put up my summary. And QCD gave us, among many other things, a very rich window into the physics in Yang-Mills theories. And these theories are connected to gravity in very surprising ways. And that means that the technologies which we worked hard to develop for QCD are also bearing fruit, even in subjects that are quite far removed from the quantum frontier, maybe not quite as far removed as the cosmological correlators that Babis was talking about, but still quite far. Now, the current generation of gravitational wave observatories will probably be running until the end of the decade, maybe into the 2030s. And assuming everyone gets their act together, there will be new terrestrial and space-based observatories that should be coming online in the early to mid 2030s. And the work that is linked to them and that is preparing for them will, I think, keep theorists very excited and occupied for many years to come. And I think the observational physics will be very rich as well. So I think there's a lot of excitement to look forward to. Thank you.
People on the Zoom, if you have a question, just unmute and ask your question. Thank you.
So, yes, so thank you.
Could you explain how you went from
the amplitudes to the one-body Hamiltonian? I mean, the non-relativistic reduction, how do you actually do that?
So you can, actually the person who should explain the technical details, if you're interested, is sitting behind you. But
Okay.
but
Discuss it privately.
I think
Okay,
that you can, of course, take the perturbative scattering amplitudes, the relativistic ones, and do a non-relativistic expansion if you want to, match in more detail to for example, if you're taking the one-loop calculation corresponding to g squared and you want to understand the detailed matching, you can simply do the non-relativistic expansion and match term by term to the Pn.
Right. So in this regard, I mean, are there any potential advantages to thinking in terms of sort of this in formalism as opposed to the S matrix?
So, in a sense, this kind of observables-based formalism that I outlined at the end is an in formalism.
Okay, very good. Yeah.
But and initially, when we started out on that path, then I thought, yes, we would have to learn Kaldich and Schwinger and develop the whole machinery. But I think it's possible to do that, but I'm not sure anymore that it's really essential. In that the observables that real-world observers are going to measure are at spatial infinity. So if we lived in some other universe and we sent people all the way into the black hole, then sure, you might want to calculate the actual orbits or things like that. But we're only observing that indirectly. And so it could well be that standard on-shell technology, essentially, which is letting you compute observables at infinity, is actually enough for practical purposes. That said, I think that it may be interesting to look in more detail at formalisms that let you compute not just asymptotic quantities, but things that are at finite time. It's just that it's not certain that you need to do that.
Yeah, I mean, in weak coupling, I mean, there is a direct, simple match between the two. It just gets harder when you go to strong fields.
Well, so it's an interesting question as to whether there's some potential to do not the kind of logarithmic resummations that we know about in QCD, but there are other kinds of resummations that will let you match better to, let's say, numerical relativity. And certainly, if you compare the actual waveforms coming out of numerical relativity for the typical binary black holes, and you compare them to the doodles that Kip Thorne wrote many years ago, they're actually much simpler. And that's not a guarantee that you can sneak up on them perturbatively, but at least it gives you some hope that you might be able to.
Okay, thanks.
So we have time for one more question.
So you described like an approach to the conservative part of the problem.
So the first part is matching conservative. The second part is everything. There's no division.
So I was just asking, is there an amplitudes program for the far zone?
So for example, this computation of the waveform does include everything. There's no separation of conservative and non-conservative there. Mm. I mean that's essentially what the 5-point amplitude is doing, right? You have the scattering of the particles, and then you have the emission of the graviton. And the graviton, so the graviton is ultimately going to build up a coherent state, and that's what's going to turn into the classical wave. But you can capture much of the physics just from single.
I was thinking that these states would exist already in cuts of 2 to 2. Already in a cut of a 2 to 2 diagram, there will be a state which looks on the cut like two black holes and a graviton?
There are contributions like that at higher order, sure. But if you actually want to compute the waveform directly, then you need to have the radiation not just inside the cut, but escaping out to infinity. And what probably will happen, I mean, we understand the words, we don't understand how to do the calculation, that there'll be some resummation that's an analog of a Coulomb resummation that will let you analytically continue that to the bound state regime.
Okay, well, let's thank Dave and move.